This video, we're going to review chapter 7.1, the area of a region between two curves. We talked about this in Calculus 1. We're just going to come back and review it before we talk about some other topics from chapter 7 that are related. So our objective here, again, review to find the area of a region between intersecting curves using integration. So remember the basic idea of integration. We can find the area between a function f of x and the x-axis if f of x is positive and 0 is less than a is less than b. Then we can use representative rectangles that are the height of the function here. We're going to integrate the function f of x dx from left to right here from a to b. We'll use the fundamental theorem of calculus to say this is the antiderivative at b minus the antiderivative at a to calculate that area. So that's great. But what happens when we dip below the x-axis here? And the integration technique would give us a negative answer for this area. If f of x was equal to 2x from x equals a is -2 to x equals b is +1 here, where a is less than 0. We're thinking about over here is specifically a problem for us. We know by geometry that the area between the function and the x-axis can be given by, if we find the area of this triangle plus the area of that triangle there. I'm just gonna ignore the sign of this being a -1 and a -2. I'm sorry, a -2 and a -4. Like that. I'm going to ignore the signs and say that that's a distance of 2 and that's a distance of 4. So when we come in here, that side has a length of 2, that side has a length of 4. Half of 2 is 1, 1 times 4 is 4. We're in units squared because we're in area. Then this side is 1 and this side is 2. Half of 1 times 2, half of 2 is 1. So 4 plus 1 is going to be 5 square units. But that doesn't match if we would just try and take integral from -2 to 1 of 2x dx. Why not? Because this is really a vector quantity, not a scalar quantity. It pays attention to whether we're above or below, and things below zero out with things that are above. So to fix that, we're going to have to actually change the sign of the function here that is going where it's going below the x-axis and make that negative, so that it looks like this, looks more like an absolute value function. And so now we're going to have the function f of x equals -2x between -2 and 0. And we have the function g of x equals 2x between 0 and 1. And we're going to integrate those two pieces individually and then add them together, and we're going to get the same areas of 4 and 1 that we add together to get 5. Again, we did all this in the Calculus 1 notes, so you can go ahead and back there and watch that video for a little bit slower example of this if you want. I'm just going quick because this is a refresher. What we're going to look at next is this area between two curves. Between A and B here, that if we look at the area that is under the red curve and the area that is under the blue curve here, we want to take the blue minus the red, and we'll get what's in purple here, which is represented by this green rectangle that would slide along here from left to right. So upper function is f of x there. It's the bigger y values minus g of x is the lower function down here. That's going to give me the smaller y values. And we're going to integrate both of those from a to b. So we're going to actually take one integral from a to b that's the difference of those y values dx. How can we apply this concept to the previous example, well, I can choose my second function here to be g of x is equal to 0. And then if I have upper function minus lower function here, 0 minus 2 of x gives me the negative 2x on the interval from negative 2 to 0. F of x minus 0 is going to be f of x on my interval from 0 to 1, which works out perfectly with what we had up here, that we had negative 2x from negative 2 to 0, and we had 2x from 0 to 1. We get the same integration. We get the same answers here of 4 units and 1 unit that we add together and get 5 units. We just switched 1 and 2 here. 1 had been over here and 2 over there. They switched places in this example here. All right. So notice that how the area between curves interpretation takes care of the required negation of negative area. This means when calculating area between curves, we won't have to worry about portions of the graph that exist in negative land, because we won't get that if we're always doing upper minus lower. So in our next example, this is going to be example 1, a region lying between two intersecting graphs. This is typically what we want to do. We want to find this bounded region between the two curves here, between the points of intersection. So we set the functions equal to one another and solve to get the points of intersection. So when we set 2 minus x squared equal to x, since those are my two functions here, then we're going to bring everything to the right so that the x squared term here will be positive, and we get a polynomial with a leading coefficient that's positive. X squared plus x minus 2, we're going to factor that into x plus 2 and x minus 1. Then we set each factor equal to 0 and solve. We get x is negative 2 and x is 1. There's my points of intersection at negative 2, 2. I know the y coordinates also negative 2 because y equals x in this case. And 1, 1, same thing. It's the identity function, so x is equal to y there on that point. I'm going to integrate between negative 2 and 1. And the upper function is going to be f of x, and the lower function will be g of x. So we're going to write this as 2 minus x squared minus x dx. And then we're going to just drop those parentheses. They don't do anything. And we're going to integrate piece by piece. So when we integrate 2 dx, we get 2x. When we integrate negative x squared dx, we get negative x cubed over 3. And when we integrate negative x dx, we get negative x squared over 2. Evaluate all of that from negative 2 to 1. And we get negative, or 2 times negative 2. I'm sorry, 2 times 1 is 2 minus 1 cubed over 3. That's going to be 1/3. Minus 1 squared over 2 is going to be 1/2. So we've got this part right here right now is going to be capital F of 1 minus, and then this part over here is capital F of negative 2. So 2 times negative 2 is going to be negative 4. And then negative 8 over 3 times the negative 1 is positive 8 over 3. So we have negative 4 plus 8 over 3. And then we have minus 4 over 2 is going to be minus 2. We are subtracting that, so we're going to change all of our signs here. So that's going to be plus 4 minus 8/3 and plus 2. Let's add the things together that are alike here. So 2 plus 2 is 4, plus 4 is 8. And then negative 8/3 minus 1/3, that's going to be a negative 3. And then minus 1/2, that's 5 minus 1/2. is 10 halves minus 1 half. That's going to be 9 halves square units. So to find the area of a region between two curves, if f and g are continuous on the interval from a to b, closed interval, and g of x is less than or equal to f of x for all x in closed interval a to b, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is integral from a to b of the quantity f of x minus g of x dx. Be cautious about intersecting points of f and g where the functions may switch places on which is larger than the other for various subintervals, and you may have to add regions together. For example, we're going to have area 1 here and area 2 here, and in area 1, f of x is greater than g of x, and in area 2, g of x is greater than f of x. So if we did not have this picture, we would have to find the points of intersection here and then test the regions to see which one was bigger. So between these two regions from, if I list the zeros in order from -2 to 0 to 2, between here, f of x we'll find is going to be greater than or equal to g of x. And we find that by plugging in something in between like -1 and seeing that 6 is bigger than -3. So f of x is always going to be bigger than g of x. In this region, we're going to see that g of x is greater than or equal to f of x by plugging in a number like 1 that's between 0 and 2 and testing, and -8 is smaller than +1. +1 is bigger, so g of x is bigger on that entire interval. That tells me my order of subtraction. I think you all know, set them equal to each other, bring everything over to one side that makes the leading coefficient positive, factor out your greatest common factor. We have a difference of squares here, so x squared minus 4 is going to break down into x plus 2, x minus 2. Set each factor equal to 0, and that's where the 3 zeros came from that give us the points of intersection here. X equals 0, x equals -2, x equals 2. And I want to look at them from left to right, so -2, 0, and 2. Well, it doesn't look this way here. This is an odd function right now, so there's going to be symmetry there. That's going to help us in a little bit, that we're going to have just as much area below and above, but this is the this is going to give me an even function when I integrate it, and we'll be able to just use half of it to be able to get our answer, because we can double the area of one of the pieces, probably this piece that has the positive number, so we don't have to deal with the negative. So if we didn't realize that though, let's just keep going and figure out all of it. So if we have f minus g here, then we're going to have 3x cubed minus x squared minus 10x minus the quantity of -x squared plus 2x. That's my f minus my g. And I'm going to get a positive x squared and a negative x squared that will zero each other out. And I get 3x cubed minus 10x minus 2x gives me 3x cubed minus 12x. When I integrate that, I get 3/4 x to the 4th minus 6x squared. The 2 goes into -12 6 times. And then I have over here, I'm going to add to the other region, and I have -x squared plus 2x minus 3x cubed minus x squared minus 10x. So when I distribute this negative, this is going to be a -3x cubed, then -x squared and positive x squared here will zero each other out, and plus 10x. So everything has the opposite sign here is what's going on. So this is going to be 12x minus 3x cubed dx. And we're going to integrate that and get negative 3/4 x to the fourth plus 12x squared over 2 is going to be 6x squared. So, and we see opposite limits here. Like I said, we could use the fact that that's going to give us symmetry to help us only need to do like half the work. But let's go ahead and let's put 0 in here. This is going to be 0 minus 0 is just a 0. Same thing when we put 0 in over here, that's going to be 0. So let's look at the interesting pieces we're going to need to subtract because of the fundamental theorem of calculus. Put in our -2, 3 times -2 to the fourth over 4 minus 6 times -2 squared. And that's going to be -2 to the fourth is 16. 16 divided by 4 is 4. 4 times 3 is 12, but I have a negative on the outside, so that's going to be a -12. Then this is going to be -2 squared is 4 times -6 is a -24, but when I distribute that negative, that makes this a positive 24. I come over here, and this was 6x squared, and I plug 2 in here. This is 6 times 4 is 24. Plug 2 in here is going to be 16 over 4 is 4 times a -3 is a -12. And we already said if I put 0 in there, I get 0. So this is going to be 24 plus 24 is 48. -12 and -12 make a -24. That gives me a positive 24 square units right here for my final answer. Right. So let's go ahead now and look at example 3, where we're going to use horizontal representative rectangles and find the area of the region bounded by the graphs of x equals 3 minus y squared. That's going to be this piece here. And x equals y plus 1 is going to be this line here. And the reason we're going to use horizontal rectangles is because this parabola is always to the right of the line. I do not have a consistent function that's always upper and lower in the vertical direction, but I have an upper to the right and a lower to the left now, and that makes my life easier if I integrate over ranges of y. So let's again set the functions equal to each other. They're both equal to x. Set the function of y part equal to each other. 3 minus y squared equals y plus 1. Bring everything over to the right-hand side. Y squared plus y minus 2. And we factor y minus 1, y plus 2 is going to give us y equals positive 1 or y equals -2. So y is a -2 and y is a positive 1 there. If we want to find the x value, it's easiest to use this linear function to do that. So y equals -2 plus 1 is a -1. X equals -2 plus 1 is a -1. And then if x equals, if y equals 1, x equals 1 plus 1 is 2. So we have the point 2, 1. And we have the point -1, -2. All right. I'll need those x values in a little bit when we try and do this the other way. But for right now, I just need these y values, and my rectangles are going to be stacked bottom to top, and are going to go from left to right here. Upper is going to be at the right-hand side, lower is going to be at the left-hand side. So upper function is the parabola minus lower function is the line. dy is going from -2 to 1 right there for my limits of integration. It's -2 to 1, and then distribute this negative sign as a -y and a -1. Combine my like terms. 3 minus 1 is going to give me 2. Then I'm going to integrate each piece. I get 2y minus 3y cubed over, or minus y cubed over 3 minus y squared over 2. Stick in my upper limit here. 2 times 1 is 2. -1 cubed over 3 is a -1/3. -1 squared over 2 is a -1/2. Go ahead and stick in my lower limit of -2. 2 times -2 is a -4. -2 cubed is a -8 over 3 times a -1. That's plus 8/3. And then -2 squared is 4 over 2. So that's plus 2. Is that right? No, -2 because that was positive. That's negative. So that's -2. So we're going to change our signs because there was subtraction that was out here. That's 4 minus 8/3 plus 2. So that's going to be 6 plus 2 is 8. And then minus 9/3, that's going to be -3 minus 1/2. Be 5 minus 1/2 is 5 over 1 minus 1/2. 10 halves minus 1/2 is 9 halves units squared. So I don't know if you noticed this, but that's basically, it's actually the same thing as example 1. We just turned example 1 on its side, kind of, and got the same answer there. It's the same area, just a horizontal area instead of a vertical area, but this is just exactly like example 1. Now, alternatively, we could attempt to modify the problem to use vertical rectangles and set up the integral. We're not going to try and solve it because I just want you to see that this is going to look really ugly and you're not going to want to do it this way. And there's sometimes one way is preferable to another way, and we want you to be able to recognize which way is going to be easier for you based off of the functions that you have. So in this case, if we wanted to go upper function, lower function, we'd have to split the graph right here. And I'm going to try and pick a darker color purple here for you. Maybe that helps you here, that's a little darker. And I might want to try and get something a little lighter color pink here for you, just to give some more contrast. Okay, so G is pink and f of x is purple there. I think that helps to get a little bit darker color like that. This may even be darker yet. That's good. There we go. All right. So we want our f of x, we want to be this dark purple, and g of x is going to be this pink color, and we've got the green rectangle that's vertically, and then we've got h of x is going to be that orange color there. So we have upper function as h, lower function is g, orange minus pink, and that works out to this point of intersection right here that we need to find, where h of x crosses purple function f of x. So set them equal to each other. That going to have to solve for y, which we've done over here. If x is equal to 3 minus y squared, we need to make that x minus 3 equals negative y squared, and y squared is equal to negative x plus 3, or 3 minus x. So that gives us a y1 of positive square root of 3 minus x, and a y2 of a negative root 3 minus x. And this is our f of x is the upper piece, and our g of x is our lower piece. This is our purple function. This is our pink function. When we solve for y for the line, if x was equal to y plus 1, then y is equal to x minus 1. That's our h of x. So let's now set purple function equal to orange function and see where they intersect each other. Well, we already know from up here where the points of intersection are, but pretend that we don't have that and we needed to find it. Here we would have to square both sides. And then we would have to x squared minus x and then 1 minus 3 is a negative 2. That's x minus 2, x plus 1, x equals 2, or x equals negative 1. I'm on the right-hand side over here of 0, so I know x equals 2, and that was extraneous. That happens sometimes with these, but we already knew that x was 2 and y was 1 there. 2 minus 1 is 1, so this is the 0.21, and then I'm going to set h of x equal to g of x, and I would get h of x equal to g of x, and I get the other half here when I square both sides. 3 minus x is equal to x squared minus 2x plus 1. Again, I get 0 equals x squared minus x minus 2. 0 equals x minus 2 times x plus 1. X equals 2, or x equals negative 1. This time I want the x equals negative 1 piece. And when x equals negative 1, negative 1 minus 1, to get the y piece would be negative 2. And there it is. And the vertex of the parabola over here is at x equals 3, if I need that. We see that it stops. It has to have a domain of x less than or equal to 3. So that's at 3, 0. If I need that for some reason, there we go. So now we're going to go from x is negative 1 to x is 2, and we have h minus g dx. Then we're going to go from 2 to 3, and we're going to have purple is f of x minus pink is g of x down here, dx, and we're going to set that up here as there's my h of x is that line, minus my g of x is this bottom half of the square root function. So that's negative 1, 2, and then this is going to be x minus 1 plus root 3 minus x dx. And then this is going to be plus, and I'm going to get 2 of these same things here added together. So this is going to be 2 integral 2 to 3 of root 3 minus x dx. Not the worst thing that I've ever seen, but definitely not as nice as doing it with horizontal rectangles there. This piece is particularly ugly. This one isn't so bad. But if creating horizontal rectangles makes your life easier, then why not do it? And so next time we're going to come back and talk about cross-sectional areas and solids of revolution. And we're going to focus in on 7.2, which deals with the disk and washer methods with perpendicular, where your rectangles or your representative area is perpendicular to your axis of rotation. And want to take something that's two-dimensional, spin it around an axis of rotation, and make something three-dimensional. And that's something, that line that we're going to spin it around is going to be perpendicular to our representative area, or our area is going to be perpendicular to our axis of rotation. All right, we'll come back next time and talk about disk washer method. See you for the next video.